Welcome back, Chemistry 30. This is the start of the Unit 6 Acids and Bases section. So this is booklet 19.1. And what we'll be looking at here is define and provide example of acidic solutions, basic solutions, Arrhenius model, Bronsted-Lowry model, conjugate acid, conjugate base, conjugate acid-base pair, and amphoteric. Identify some acids and bases which are used in common household products. Identify physical and chemical properties of acids and bases. Classify solutions as acid, basic, or neutral. Compare the Arrhenius and Bronsted-Lowry models of acids and bases. Describe the Bronsted-Lowry definition. Identify conjugate acids and bases formed in acid solutions. And describe the ionization of polyprotic acids and substances that are amphoteric. So first of all, some properties of acids. Sour, it tastes sour, for example, lemon juice, etc. Can be corrosive and also conduct electricity. Very good conductors. Bases, they taste bitter. So if you imagine, so sour versus bitter, the hop taste in beer, that's a bitter taste. So it's a little bit different than sour. Slippery, think of soaps. That slippery feeling is a characteristic of bases. Also corrosive and also conduct electricity. And then we look at two common reactions with acids. First of all, when acids react with metals, so elements on the left-hand side of the periodic table, for example, magnesium, zinc, etc. So I chose hydrochloric acid here. If you see here, so 8 acid compounds are characteristic by having a start with an H here. The compounds start with H, and it's a single replacement reaction here. The metal replaces the H, so now magnesium chloride, and remember magnesium is 2+, chloride's 1-, so I have to have 2 chlorides for every 1 magnesium, that's why that's there. And then hydrogen is exchanged and it's off by itself. It's a Hofbrink element. It's hydrogen gas. It exists as H2. So hydrogen gas and a salt or ionic compound is what is produced. A metal and a non-metal compound consisting of those ions. So that's characteristic of acids with metals. A salt or an ionic compound with hydrogen gas. Another common reaction is acids with carbonates. We get as a product water, carbon dioxide gas, and also a salt or ionic compound. So for example, sodium bicarbonate, HCO3 is a negative ion. So here we have baking soda combined with an acid. And if you take a look at what happens here, we have the positive ion of the carbonate and the negative ion of the acid come together to make the ionic compound. And we also have water being produced and carbon dioxide. Okay, so those are two characteristic reactions of acids. One with metals, where we get hydrogen gas produced. So if you want to make hydrogen gas, have a metal combined with an acid. Or here's a common one used in baking, making nice fluffy bread by the carbon dioxide gas that's produced when baking soda reacts with an acid, which of course with baking we'd be looking at vinegar. Okay, so looking at these ones, I'll let you try these ones here. I think you have acids named on your periodic table, so sulfuric acid, calcium metal. So here it's a case of a metal and an acid. So maybe pause the video and see if you can try these next few questions to see if you can follow the format from back up here and determine what the products are. Okay, so over here, calcium metal, sulfuric acid is H2SO4. So the calcium and the hydrogen replace each other, and we get hydrogen gas. And then calcium is 2+, sulfate is 2-, so they come together in a 1-to-1 ratio, CaSO4. Here we have potassium, hydrogen, oh, it's a carbonate. So it's going to use this form here. With chlorous acid, if you recall from naming acids, if it ends in OUS, it used the ITE ion, so it's the chlorite ion. So if you look at your pink sheet, ClO2 minus is the ion that is part of chlorous acid. Potassium and hydrogen carbonate, HCO3. Hydrogen carbonate or bicarbonate are the same things. It's this, you call it hydrogen carbonate or bicarbonate according to your pink sheet. So what happens here, the metal of the carbonate combines with the non-metal group, the anion of the acid, to make your ionic compound, so KClO2, and the other two products, of course, carbon dioxide gas and water. And I think it's already balanced, so we don't have to worry about that. Okay, so two common reactions of acids. Other indicators that determine whether an acid or base is present, some of them you may have used in grade 10 science or Chem 20 or grade 9 science. When looking at indicator paper, litmus paper, acids turn litmus paper red. So if you're using red paper, it stays red. If you're using blue paper, it turns red. Whereas base turns litmus paper blue. So that's another visual cue to determine acids and bases. Also, if you look at one way of looking at acids and bases is in terms of hydrogen ions and hydroxide ions. So as mentioned here, acids begin with H, so hydrochloric acid, sulfuric acid, etc. If the and some bases are characterized by having OH minus ions present. So if we have more H ions than OH minus ions, that is considered acidic. If we have more hydroxides than H's, then it's basic. And if we have an equal amount, it's neutral. I can't remember if I made this change in your booklet, so change that to neutral there. Another way of expressing a hydrogen ion is in terms of a hydronium ion, H3O+. So if you ever see that, it means the same thing as H+. If we look at what happens to water in a solution, or just simply like a glass of water, some of that water breaks down into H pluses and OH minus ions in equal amounts. Therefore, the solution is neutral. So one water molecule, we can get one H and one OH. Or if we had two water molecules, we can imagine it as one of these hydrogens attaches to a water molecule, leaving OH behind. So you can see here that H plus and H3O plus have similar characteristics. Now how does that happen? So what I've shown here is a water molecule, the bonding. So one oxygen bonded to an H, bonded to an H. An oxygen has 6 electrons in its outer level, 2, 4, 1 for to bond with the H's electron and 1 to bond with this H's electron. So it has 2. So what happens here is that it makes room for an extra H. So one of these electrons would leave, so it basically lost an electron, so it became more positive, and that H would attach to that empty spot. Whereas the water molecule that lost the H, it would have an empty spot where that H once was, so another electron comes and attaches itself, it becomes more negative, so OH minus. So that's kind of the rationale as to how that happens. One H going from one water molecule to the other, making the hydronium ion, H3O+, and the hydroxide. So you can see here where that H was attached, an extra electron came and found that spot. Okay, I think we'll stop right there. So that's the end of part 1. Part 2, we'll look at other definitions of acids and bases with chemists from a long time ago, how they defined acids and bases, and then we'll look at dissociation of acids. Okay, see you soon.